So yeah, my name is Lukas. I've been working at the Erlang JIT team at Ericsson as a consultant for the last 1.5, almost 2 years now. And the last year or so, I've been privileged enough to be involved with the creation of an Erlang JIT compiler, or the start of it anyway. I've been doing some research and planning, and I'm going to present the research that I did, my findings, and some part of that, and also present the prototype that we've done and so far that we've come. I'm thinking we're still developing a prototype, so there's nothing really done yet, but it's, I think the guy working on it is working on it now, or actually sleeping in Sweden, but you get the idea. So I'm going to talk about an Erlang JIT compiler. So let's put it there. So the general outline of the talk is I'm going to talk a bit about JIT compilers in general and see what different JIT compilers there are and how you do them. I'm going to talk a bit about how the Erlang virtual machine handles code today and how it works. I'm going to talk about the idea we had and what we want to do. And then I'm going to show what we're doing with the prototype and what the tools we're using and how we're planning on to go forward and what the end result will be. So when talking about compilers, you have, I've like to divide it into 4 different parts. You have your normal compilers that are basically Erlang VM, GCC, different kinds of ahead-of-time compilers where you're basically just typing your command line and you're compiling them ahead of time. Hype is another example of that kind of compiler, so you're doing some kind of ahead-of-time compiling. You also have something that's called that I like to call an on-demand JIT. So here you don't have an interpreter as you would do in Erlang or in Java or something like that. So you're compiling your code directly as you're executing it. So you don't have an interpreter. You just have this bytecode that you're running, and then as soon as it gets executed, you compile it to native. And some examples of that is the Microsoft.NET, the CLR is using that technology. The V8 JavaScript engine for Chrome is using that. And I get Node.js as well in the end. So it's using that, so it's compiling directly. Method-based JIT is what the JVM is famous for. So the JVM and something called Jägermonkey, which is the new Firefox JavaScript engine, is using method-based JIT, which is basically you take a compilation unit of a method and compile all the branches within that method to native code and optimize it for the specific architecture that you're running. And you have something that's called trace-based JIT, where you have a lot of different platforms that are using this, and it's kind of the hotbed right now of JIT compilers, what you're using. And there you're following the execution pattern of your program as it's executing and taking the specific branches and the paths that you're using. So I'm going to try to explain the differences between what you would do with the method-based JIT and the trace-based JIT, as we already have an interpreter in Erlang. So doing an ahead-of-time compilation or a on-demand compilation would sacrifice all the work that we've already done with the Erlang VM, so we want to keep that. So we're focusing on one of the 2 options below. So let's think about this kind of simple example that I've stolen from a presentation by PyPy. We have put a lot of work to put the Erlang VM and fine-tune it to the way it is. And we don't want to sacrifice that work that we put in, and we want to reuse as much as we can to limit the cost of producing this JIT compiler.
You don't have to compile everything.
No.
Compile some files.
Yeah, precisely. But if you're compiling all the branches, you can't do as much optimizations as before. If you want to argue with me about the different points, Kostas, you can do that afterwards. We don't have to do that now.
It's not, but you don't sacrifice anything.
Your viewpoint. Yeah, well, let's talk over beer later. You can see the different points. So let's talk about a simple example about what you could do in the different kinds of compiling. So we'll talk about this very simple function and what you might do in 2 different approaches of doing JIT. So if we start out and see what we could do with a method-based JIT, let's see. Still getting ahead of myself. So the basic Erlang instruction for doing an add looks something like this. You're checking the types of what you're using at the moment. So you're checking if both types that you're adding are smalls. If it's a small, you untag them and you add them, and then you tag them again. So you do that kind of things, and you have to, again, check if the result that you get still fits in the small or if it's overflown. And if it's either of the two types are not smalls, you're going to do a mixed add, or if you're overflowing, you're going to do a mixed add. The mixed add looks something like this. So you have to take care of floats, you have to take care of big nums, and you do bad arith if you get atoms or lists or whatever in your add instructions. So something like this. So if we take a look at how you would JIT compile something like this for a method-based JIT, we would take the two different parts, the two different instructions, and inline them into a function call. So you do the add B, C, and Y, and then you do an if statement, you insert the entire code, you have the entire, all the branch logic and everything, and you compile this to native code, and you do it for both of the instructions after each other, so that you can do optimizations for this method unit. And of course, and then you have the return at the end, so it's exactly the same semantics. And of course, I haven't inserted here the mixed add, which would also be part of this part, so it would be quite a big space of operations that we would have to do here. Now, for a trace-based JIT, if we're following the semantics there, we want to follow the way that the program works. So what we do is that we check to see what's happening. So the first thing that's happening is that we're checking, is this a small? So we record the check that we do and put a guard in place that says, verify that this is still true. And if it's not, we're going to fall back to the interpreter mode and do the same thing in the interpreter. And then we follow through all of the different parts, checking what we're doing as we're doing it, and creating a string of operations. So we get a sequential string where you have a lot of guards asserting the assumptions that we have done in different parts, and executing the code that was actually executed. Not all of the different paths, but the path that your code took as it was executing. And we add the return at the end, and we have a program on the left side there that has sequential parts of programs, and we have on the right side, you have the method base. So that's two different ways of doing them. They have different pros and cons, these two. To point out some of the pros and cons, I have a bit more advanced example that I'd like to show you. So let's say we have detected that this add here is what we call a hot path. So it's something that's executing a lot in your system. So this is not going to be happening to every function call all over the places where your code is executing the most. This is where we decide to do these things. So this function is executing a lot for some reason. Now, if we're going to take this function and do a method-based JIT analysis on it, we're going to do very heavy inlining. So as much inlining as we can. So generally, we will put the functions that we had before, we put it in there and say, okay, so we do the add once with all of the different variables set there. And then we add all of the variables again, and then we do the same thing again. So you would just JIT compiled, well, this part of the code. So you have that, and you can do optimizations on this. And again, the big arith and the mixed arith isn't part of that. So you have a huge space. Doing the same thing for a tracing JIT would end up being something like this. So you have a long string of commands that you're doing guards, checking in all the different places, and as soon as a guard fails, you're jumping back to the interpreter. So you only have to focus on the actual path that the process you're executing took to do the different parts. Now, I sat down and applied some common optimizations to this once, such as common sub-expression elimination, constant folding, and some other parts. And you end up with code which is a lot smaller and a lot faster to run. And you've removed moves, and you've untagged variables, and done lots of different parts. So this is where I think, in a way, that the tracing JIT compiler would be really good to use. And that's also what we're trying to do now, to do something like this. Don't care about that. So some pros and cons about the different parts. So the method and or function-based JIT has usually a smaller memory footprint for more code. So you have a greater coverage when you're doing a method-based JIT because you're covering all the different paths that you're executing in the parts. Unfortunately, you can't do as good dependency analysis when you're doing method-based JIT. So if you do a computation and then something else depends on it, it's very hard to figure out what the dependencies are, and you always have to keep your entire state space available to you. And it's hard to do unboxing optimizations with your integers and floating points and whatnot. Not impossible, but it's harder than to do it in a trace-based. the trace-based JIT only compiles a very small parts of your code. So if you have very branchy code, you're going to suffer. So you have a lot of if statements, lots of case statements within your code that you have like 33% chance that it's going to take any branch. It's going to get very branchy very quickly and taking all different parts. And that will hit performance of the tracing JIT. And that's one of the reasons why the recent Firefox JavaScript virtual machines is moving more to a method-based and trace-based JIT, because they're seeing their code is too branchy that they're running, so they can't really do a trace-based JIT based on that. So they're doing some kind of mix, which is probably, if you have the time and the money, you can do a mixed approach to that.
Does branchiness apply to pattern matching as well as?
Yeah, I mean, if you're a branch when you're coming down to Erlang code is not a pattern match, it's just a branch, it's a case statement. So, I mean, I don't know if you've looked at the Erlang compiler or anything, but if you're doing pattern matching and you do case statements, the code will be the same. So it's just doing case statements anyway. So it's the same thing. So that's the general idea about JIT compilers, comparing different parts. So let's have a look at how the Erlang VM works today and what it does. So let's take another example, a factorial function that I hope I wrote correctly. That does some checking. So you have your Erlang source code. You compile this to Erlang Beam code. That looks something like this. It's not really important, the layout of the code, but you have two different clauses here. So you have a label 2 and a label 3 in different clauses, executing different code, and you do lots of moves and call some bifs and things. The next step we take is that this Erlang Beam is loaded into the Erlang VM, and then it looks like something like this. So you have, you can use, there's a function called debug, I think it's called, that you can get this information out, so you can see what the actual code loaded looks like. And this is just a copy-paste from that, so it looks exactly like that. And don't know if you remember, but from the previous slide, you won't remember, we had some parts that looked like you had to do the move and a call. So the loader does some optimizations at this level. So you can see the move and the call has been transferred into a move and call operation. So you get higher speed because you specialize this function. And it's also saying that, so we have a move that's from an X register to a Y register. We do this in a special operation. So this means that there's a lot more different operations in the Erlang VM than in the actual binary code. I don't know the exact ratio, but it's a lot more. And this is all done automatically, so you don't really have to care about it. So let's have a look inside the Erlang emulator loop and how it processes this code, these commands that we have here. So every command is processed in the code. So when we start up the Erlang VM, you start in the main function, which is somewhere in the system, so in the sys folder. So it does something, and it creates schedulers. So depending on your OS, it creates different schedulers. And it depends on the number of cores, then it creates a scheduler for each core or whatever you configured. And then it enters a function called process main within beam emu.c. And in here, you have the entire interpreter is in that source file. It's a very big source file with lots of code in it. And there you have you have some include files and things with the different parts. The general execution pattern that happens is that you first check when you're loading your code, so you're checking this process that is running right now, do I need to reschedule another process? And then you say, yes, I might need to schedule a process. If you don't have one, you schedule one. If you're already on one that's used all its reductions, you take another one. We'll go back to the same thing. Is the module that I'm running, is it there? If it's not, then you fire an exception, and the error handler kicks in. It loads the module, and then you go on executing your code. So you go yes, and then you go back again, and you check if the loading of the code actually takes reductions. So you might have to be scheduled out. So now you have the code, you should do it, and then you're executing the next instructions until you run out of reductions, and then you're back in the loop again. So that's a general idea about how the different instructions work. And of course, this is a very simplified model. You will have LinkedIn drivers being called all over the place, and you will have sockets, selects being called, and so on. This is a simple picture of what the Erlang VM looks like today. So hopefully we can compare and contrast this to what we want to change it to. So let's have a look about the idea and what we want to do. We want so the requirements that we set upon us was that we wanted something that would work across modules, that you could optimize across module borders. So you wanted to be able to create traces that work across module borders and keep the same semantics as before. You can still load new models and do external calls and reload the calls, but you want to have something that works across modules, so we can do optimizations there. So for instance, if you have a fun that you're using with the lists module, you want to be able to have a trace that goes through the fun in your code into the lists module, creates a specific trace for your code. We also want to have really fast switching between the JIT compiled code and the actual interpreter, so that you can have small pieces of code running and then quickly going to and fro. And also if you happen to hit an unfortunate path, so that you get a lot of branch outs from your stream of instructions, you will be fast back into the interpreter and executing in that part. We need the code to be preemptive so that we can schedule out the code as it's going wrong, and we can also go out to the interpreter. We wanted to be able to create a prototype really fast, and we wanted something to be easy to maintain. So what we're doing is that we're creating, as I said, a tracing JIT compiler for Erlang. Right now we're focusing on recursive function calls, but that's probably going to be centered on the actual call, so that you're doing calls within that. There's probably going to be, we're working with receives and these kind of things, so you get a trace centered on the receive and doing sends and so on later on. We want the JITted code to work as much as possible in the interpreter, so in manipulating the variables that are in the interpreter. The general idea right now anyway is that we should abort any JIT pass if you get scheduled, the process gets scheduled out for another process or anything. We just abort the JIT pass and you go on back to the interpreter. So as long as you're running within your reductions, you're within the JIT pass, but as soon as you're scheduling out the process, you have to change into the interpreter. This is because code loading has to work. Yeah, and then you have, the idea also is to have different optimization strategies depending on how long the trace has lived. And we're using Erlang VM to do much of the heavy lifting of this project. So let's have a look at the prototype and what we're doing. So I'm not actually doing any of the coding of this, so the specific details I don't really know about how it's implemented, but I know what he's doing. There's a guy at the Swedish Institute of Computer Science that is doing the work. His name is Fred Dreihammar. He sits, 2-minute walk from our offices, so we're in contact with him quite a lot. And he's creating using Erlang VM to create the traces during runtime, and is using something called libclang to bisect the Erlang emulator and create two types of emulators. I'll get more to that later, how that is done. Oh, I don't have the right font there. That's why it looks so wrong. Okay. Yeah, so what we're doing is that first we have a profiler. So after every function calls, we've inserted a new instruction that actually measures how many times a function is called. So every time a function is called, you will have a new instruction that gets called, and it increments a number. When that number reaches a certain point, we will say that this is a hot loop, and we will start to trace the pattern that your process is taking through that loop until it reaches back until itself, and then we'll compile that to native code and make it execute. So when n number of calls, somewhere like probably 50 calls have been done, we say, okay, we flag this process, this needs to be traced, and then we switch to our other emulator. So the other emulator we've created is like this. So we're using libclang to analyze the C code of beamemu.c. So libclang is a way of representing the syntax of C code and manipulating it. So we load into the entire C code into libclang, and then we're manipulating the AST to create two different emulators. The first thing we have to do is we have to extract all local variables from all of the different beamops. So some beamops have a local variable that it uses to store some temporary data. And in order for us to go from the JITted code to the interpreted code, we need to know what that variable is, and we need to be able to manipulate that variable as we're doing the JITted code, running the JITted code. So we extract all these and put them in a global scope in that C file. And after that, we're taking all of the different beam-ups and converting them to what's called basic blocks. So a basic block is a sequence of instructions ending with a jump somewhere. So if you have, for instance, an if statement within your beam-up, you do an assignment and there's no branch. But if you have the if statement, we're going to convert that beam-up into two different basic blocks. So one where it takes one branch and one where it takes the other branch and then the initial branch. So that's 3 basic blocks for the different parts. And these small basic blocks is what we're tracing on. So in the plain EMU, we have the normal interpreter. It's just spliced up and we've lifted all of these local variables. It works the same. We've measured the performance on this, and it's the same as the normal Erlang VM. And then we have also the beam-emu trace, which has inserted an instruction in the beginning of every basic block to record what the variables are and what the path that's taken is. So we're recording as we're going along what the path is going through. Another thing that we've changed in the Erlang VM is also that we're using a dispatch table to do code dispatching instead of using code threading. So code threading and dispatching is, if you're using a dispatch table, you have to look up in an array where the next instruction is located in the code. So you have a label in an array to look up. So you have a number, I need to go to instruction 39, you look up in an array, that's at the address this. When you're going code threading, you have the actual address of the next instruction patched into the code, so you just do a pointer jump in the code instead. So we're removing that feature in order to do a dispatch table. That way we can switch the dispatch table from the plain EMU to the tracing EMU by just changing a pointer. So that's, in order to use the two different variants, we can just change a pointer, and then the code is all of a sudden using the tracing EMU instead of the plain EMU. So if we remember, the old beam EMU loop looked something like this. So what we've added so far is that we've added a question saying, is this code JITted? If it is, then we should run the JITted code, obviously. If it's not, we're asking, should we be tracing this specific function? So has it been done that? In the beginning, obviously, that won't be the case. So we're just executing the instructions as per usual. But let's say this function has been executed 50 times, and we say, yes, we should trace this. Then we're doing the same thing, only we're recording the instructions as we're going along to figure out what the exact path is that we're doing. After, when we collected the trace, we've gone an entire loop. We create something, so we compile the trace and we link in the trace. And we go back to the question, has the code been JITted? Of course, it's been JITted. So we check out, OK, so let's execute this JIT instruction instead. So we execute the flow of JIT instructions instead of doing the generally interpreted instructions. So far, the parts that we have done are the red parts here. So we can produce traces of different parts of code. We collect the different basic blocks and what we're doing there. And Frey is working right now on putting the two last pieces together. So from now on, it's theory for my part. It's nothing of this has been done in the prototype part. So, but what I envision this will look like is that in the end, in the compile time then, we have taken the different basic blocks. We've compiled them to the intermediate representation of LLVM. And then we're sewing together these different basic blocks in the parts that we want them, that we've seen that the code has executed, so that we get a pattern with the exact same C code, so we can do this automatically. And then use LLVM to combine this to a function call, which would look possibly something like this. So you would have a function calls like call JIT for an anchor, and that's anchor 1. And then you get all of the registers that you're using as arguments to the functions. And then you get a big struct containing all of the local variables that you might have to manipulate into the function. And then you're going through the different code motions with the highly optimized code that we're using there. So that's the general idea about those parts. How long time do I have? 20 minutes. 20 minutes, oh, like that. I'm talking too fast, sorry. Some of the limitations that we're foreseeing is that, of course, as this is only for sequential code. No parallel code will be going faster. If you're having a lot of message passing in your code, you probably won't get much of a speed up. If you have lots of receives, we might be able to optimize if there's something in the message queue, but if you have to wait, you won't be getting a lot of speed ups when you're running this kind of code. When you're communicating with drivers or NIFs, in general, we can't really do much about that. So it's a big black hole, and you can't really optimize for those parts because it's C code. Hopefully, as part of this, we will be rewriting some parts of the drivers that we have to Erlang, if that proves to be faster. Hopefully, it will be. Yeah, as I said, I'm talking way too fast because I'm already done. So hopefully you have lots of questions. So what we have right now is we have a 50–60% almost working tracing JIT compiler. We've been using libclang and Erlang VM with great success. We have created NIF bindings to these tools and then been using them to manipulate the different source code. We have a lot of things that we want to do and that I envision that we would need to do. We have to do garbage collection of traces in different ways. We need to figure out what to do with receive loops and how to manage having multiple receive loops in the same trace and what's going to happen there. We need to work on the SMP support of everything, and we need to make sure that code loading works, and we have to see if we can do something about the NIFs and drivers. Maybe we can instrument NIFs and drivers to make them faster by looking at those parts, or primarily this problem would be for BIFs, not NIFs. But that is something, that's a problem for us, so we might have to do some kind of profiling on the different BIFs. And there's no end of the potential of things you can do with this kind of technology, so hopefully it will be ongoing forever and just improving performance. So since we don't have a prototype, I don't have any nice pictures like Kosti said this morning about what kind of improvement in performance you might expect or anything like that. But we're hopeful that we will be able to at least compete kind of with hype. That's our hope. So yeah, thank you, and hope you have lots of questions, because we have like 15 minutes of them. Patrick.
You talk about like branchy code, and it's not being especially good for branchy code, but that's branchy code where you actually take different branches.
Yeah.
So if you have like 99% of the cases you take the first branch, then it's not branchy from
No. Branchy code means that you're taking the branches. If you have branches that you're not taking in this tracing example, it doesn't really care about that code. It just checks if your conditions are the same again, and then it continues on. So branchy code, so the kind of code that would just be ignored is like error handling and throws and these kind of things. So it just gets ignored by the tracing. But you have to have the same semantics all of the time. So we're not changing any semantics that's happening. But you can do, we're hoping that we can do a lot of different optimizations, both using Erlang VM's built-in optimizations and then doing language-specific optimizations that we can do because we know it's Erlang, and because we know it's single assignment.
Sounds really cool. If I understand right, you're working on a prototype. Only one guy is doing the coding, but it looks like there's a ton of work to do. Is the goal that once he's done the prototype, Ericsson will beef up the team and get this stuff functioning quicker, or will it take a really long time?
It's a priority question. I don't really know about that. I mean, I would love to have like 5 guys working on this to make it work really quickly, but with the prototype, I envision that hopefully the prototype will be done after summer so that we can do some benchmarks and see if this is the way we want to go. That's not really been decided yet if this is the path we want to go. We want to measure and see if it actually gives a speed up before we're making any decisions about how we're scaling this thing up. Yeah, definitely. Lots of decisions to make.
Are you going to make this open source?
Yeah, well, yes, of course.
You will get more resources if you work with it.
Yeah, of course. When it's done, it will be default in Erlang. So yeah.
When do you think it will be mastered or available?
Before native processes. I don't know. It's it depends on how successful the prototype is. If we have great success with the prototype, it might be an experimental feature in R16. If the prototype doesn't work the way we want it to work, it could be until, I don't know, R20. If it doesn't work, it doesn't work, and then we have to step up and actually learn how height works.
There's no mechanism to preview prototypes. It's either part of the release or it's not visible.
I mean, yeah, we could. When we're done and we've done some work, we definitely could put that up and for people to look at it. And the tools that are coming out of this will open source them. So the NIFs for libclang that are quite useful. So when you're analyzing C code and these things, and I'm not sure if we're gonna. I've written some NIFs for Erlang VM already that works, so, and they're open source, so you can use them. So we'll see. Yeah.
How does JITting affect reduction counts and scheduling?
The idea here is that work is what you're measuring when you're doing reduction count. So the same amount of work will be done by a process when it gets scheduled out. It will just do that work faster. So
But doing the JITting is work, right?
doing the JITting is definitely work. So
Count towards the process's reduction count. You know, how does that
probably.
scheduling?
Probably, yeah, probably. The details of that is, we'll see. We'll break that when we come to it.
So assuming that like you are able to open source and make the prototype available at some point, do you have any internal tools maybe already or something that would help like other people to see what are the hotspots in the code? So it would be nice for the profile and like how kind of suitable my code is for JIT.
Start there's this thing called call counts that you can start the Erlang emulator with. So I think it's enable call counts or something when you're starting it up, and then you can measure the number of calls that functions are doing on the different parts, and then you can use that to do the different things, or you can use fprof or whatever to see what the hotspots will be in your code. And this is where we'll be focusing on making it faster.
At all about runtime support.
Runtime support, like, what are you referring to?
Is it going to be in the same stacks as the beam?
Yeah.
Okay.
That's the idea anyway.
Passing things to registers.
With the registers, where so I don't know if you saw the slide about where we put. We haven't done this work, so we're still experimenting with exactly how we're doing that part. The last thing I heard from Frey was that he wanted to do something similar to this. So you're passing the registers as arguments to the function in some way, and then you're putting them in there, and then as you're exiting the function, you're putting the registers as variables back into the Erlang emulator loop, and all of the local variables and all the different blocks are manipulated directly in the struct that we're passing to the different functions.
I understand correctly that this is going to be only for things that don't GC.
Sorry?
How are you going to communicate to the garbage collector the roots?
It's going to manipulate the heap in the same way that the C code that runs there right now.
It's a stack.
Okay, the stack then. It's the same C code that is running as the Erlang emulator loop.
But the C code of the Erlang emulator loop does not have anything that needs to be traced. It's just C stuff. Here you will have.
Yeah, okay, so you're thinking about the different things that are created during the trace. Or are you?
We have Erlang terms here.
Yeah, definitely. We'll create Erlang terms during it, and you will have to use the same allocation methods that you would use in the VM to put them on the different parts. And you will have the pointers to the process and the stack and all that into the actual. No, okay, yeah, I'm not sure.
At least you have to have that when you fall off the path. So if you fall off the hot path, the stack has to look like you would have done if you hadn't hit it. But if you're sure not to fall, you don't need to like create templates.
But you might, within this code, you might overflow the heap. And you might need to do
Yeah, and then you
collection.
fall off the path.
And then you use a normal interpreter to clean up your mess.
Good luck with that.
All right, yeah.
tracing information and function call counts without slowing down regular bean code?
You can't. There's about, I did some measurements on this, and there's about a 5–7% performance drop with the profiling. But hopefully we'll surpass that with just the tracing, so making it faster.
For the new VM slides, you were talking about how you were using the client library of today's analysis over VM units, spitting out being client and being JIT. Where you're just doing that sort of initial phase to generate those new files, and you're going to like build that more, or are you always going to just do updates to VM and always just generate constantly?
If we can, we're going to keep it in one and generate. Yeah, but if it turns out, I mean, it's a prototype, we're exploring. So if it turns out that that doesn't work, it doesn't work. Yeah. And that's what we're aiming for, because we don't want to spend lots of time maintaining code. We want to make new cool stuff. There's a hand under the light, I think.
That's right. I think that my limited understanding is that one of the issues with hype is that the transition between hype and non-hype compiled code is potentially expensive. And I think you mentioned that one of the goals was when JITting to not have that cost, so it's an easy transition to go back and forth. What is it about the JIT approach that's different from the hype approach that means that you don't have that same problem?
So far, there's not much of a difference, and the way that we're working now, at least, I'm not familiar with how hype does it. Really, you'll have to ask somebody else, maybe Patrick or Kostis will know. But as far as I can see it, we're more tightly coupled with the actual emulator and how we're working there. So there's hopefully will be a lesser switch in between the two. But I don't know how it's going to work out in the end, and Kostis seems skeptical, so we'll see.
It's not a matter of skeptical. I didn't understand. So the C stack is one thing.
Yeah.
Then there is the stack of the process.
Yeah.
So if you have two things, you will have to pay some cost when you are moving between one and the other. And that's exactly the thing with hype. It has a native stack and it has a if you put them together, but I don't understand how you would put them together.
Okay.
Probably you're not going to, I don't understand whether you're going to put them together or not.
All right.
Can you answer this question? Are you going to put them together or not?
Put the
stack and the process stack together?
No, the C stack and the process stack would be separate, I think, as far as I understand it. But you will manipulate the process stack from the JITted code directly, not copying it over or manipulating it anyway. Is the idea.
With JITted code, will you be able to do code upgrades and tracing?
Yeah, hopefully. I mean, yes, we'll have to. The same characteristics have to apply. And if we can't do that, we'll have to throw away the project. So you have to be able to do that. So the idea I have right now is just that you purge all the traces that are in the module that you are actually going to upgrade. So you just purge those traces, garbage collect them, and then you load the new code, and then the new traces will go through the code. But we'll see how that works in the end.
Don't you have some branching there? So if you're reloading a module, it calls another module.
Yep.
And you JIT the whole path.
You have to keep track of which module is it in, and see what's happening.
Your last slide, you had one of the things you were thinking about doing was inter-process tracing as a potential thing. What you never talked about that?
That's just a crazy idea I have that I want to be able to, like, for instance, if you're for instance, having a gen server, you know that you can do some small parts, like you're tagging your messages and you're sending them back and forth, so you might be able to do something there, but it's just crazy ideas. Yeah, but it's crazy ideas. I mean, if you have different schedulers, the processor is not going to work. So you have to do lots of things to make that work. Yeah.
Right. Any other questions?
All right, thank you.